Let's finish up our exponential functions with some word problems. Okay, so you start a new job with an initial salary of $36,000 per year. So initial salary, that's making me think about A for our exponential function. Each year thereafter, you receive a 3% raise. So seeing that 3% increase and that it's happening each year, that tells me this is going to be exponential since we're increasing by a percentage. With this, I have B equals, since it's a raise, it's an exponential growth, so we'll have 1 plus, and 3% is 0.03. So we're seeing 1.03 for B. Again, this is a case where make sure you have that 0 in there, like we're moving that decimal to the left 2 spots, because a 3% raise is very different from a 30% raise. So mixing those up will give very different incomes for this person. So make sure you move the decimal correctly for those. All right, so our formula for S of t, we have our initial value of 36,000, and then times, and we found our growth rate of 1.03, and then our variable t. So what will your salary be after 10 years? So this is just plugging in 10 for t. So we'll have 36,000 times 1.03 to the power of 10. And then we'll just go to a calculator to help us out with this. So 36,000 times 1.03 to the 10 power. So 48,380 point, and then since it's money, we'll round to 2 decimal places at 0.99. So our salary will be $48,380.99. When will your salary reach 72,000? So salary is S, so we're looking where 72,000 equals 36,000 times 1.03t, and we want to solve for t. Now, we talked about solving equations where we have the same base, but to think of a way of changing this to a base of 1.03 hurts my head, and I think it will be really tough, if not impossible. So this is where, because we don't have logarithms yet, we're going to use our graphing calculator. So you can graph it at this stage, which would be the equivalent of graphing the line 72,000 and then seeing where it intersects this graph of 36,000 times 1.03 to the t. If you want to make it simpler, you can divide away the 36,000, and that's not too bad in this case. If it was going to come out to a messy decimal, then I wouldn't do this step. But if we divide, then that's the same as 2 equals 1.03 to the t, and this isn't too bad. And then we don't have to look all the way up at y equals 72,000. Now I can just look at y equals 2, which is a little easier on our calculator window. So solving that first equation is the equivalent of solving this equation right here. So we're going to go to our graphing calculator and find a value for t. So in the graphing calculator, what I'm going to do is have the horizontal line y equals 2, and then I'm also going to graph 1.03 to the power of, and x is what we'll need to use. And as you can see, this is going real slowly. So I just need to find my intersection point, which is here. And if you, Desmos is really good about this, it'll highlight the where they overlap. So we have this intersection point of 23.452. So with that, our answer is 23.45. So I'm trying to answer when will your salary reach $72,000. I'm going to say after 23 to 24 years, because it'll be between those. So after 23 to 24 years, your salary will reach $72,000. All right. After caffeine is consumed, it leaves the body at a fairly fixed rate. A person consumes 200 milligrams of caffeine at 8 a.m. 4 hours later, about 100 milligrams of caffeine are remaining in their bloodstream. Let Q of T be the number of milligrams of caffeine in the body T hours after consumption. So we're getting these two ordered pairs, or you can think of that as like two coordinates. So we have T is hours after 8 a.m., and Q is the milligrams of caffeine present. So the idea is when T is 0, which is the same as 8 a.m., we know there are 200 milligrams present. And then they tell us 4 hours later, so 4 hours after 8 a.m., there were 100 milligrams left. So writing a formula for the function, so this is a case where we know the initial value and we know a coordinate. So we're going to go ahead and start our function with the initial value plugged in, so 200 times, but we don't know what b is, to the power t. Then we're going to plug in our coordinate, so 100 equals 200 times b to the 4th power, and we're going to solve for b. So I'm going to divide both sides by 200. So 100 divided by 2 is a half. So I'll go ahead with 0.5 equals b to the 4th power. Then I want to get rid of that exponent of 4, so I'm going to raise it to an exponent of 1/4. And I'm going to do that to both sides of the equation. And that should give me a value for b. I'll go to a calculator to help me out with 0.5 to the power of 1/4. And we get a 0.8409. So rounding to the 4th decimal place there. So, and then I'm just going to make this little check that, okay, as time is passing, it's decaying, so we have less in the bloodstream. So having a growth factor that's between 0 and 1 makes a lot of sense, because we're seeing an exponential decay. So, Q of T equals 200 times 0.8409 with our variable of T in the exponent. How much caffeine is left in the body after 4 hours? Well, it's 100 milligrams. Let's change that up. Let's change that to 2. So 10 a.m. So what we do is plug in to our function. So 200 times 0.8409 to the power of 2. And we just plug that into a calculator, and that should be about 141.42 milligrams. How much caffeine will still be in the body at 8 p.m.? So this is the idea of 12 hours later. So if T is 12, so Q of 12 equals 200 times 0.8409 to the power of 12. And let's actually look at this one in the calculator. So 200 times 0.8409 to the 12th power. So 25.0013, or maybe about 25 milligrams. Again, you can always, with these word problems, so I could write it exact here, 25.00, and I forgot what the last two numbers were, 13. So I could show the calculation and have that exact value, but when I make my sentence, I could round and just say about 25 milligrams, something like that. So you can show your exact work as you're solving, but then when you make the sentence, round to what makes sense.